Welcome. Here is a new problem at your screen. You can see it here. And that says ring in a ring. No, ring in a finger, not ring in a magnetic field. So it should be in a finger. It looks good there, but it's now in a magnetic field. So we have a problem that says a thin wire ring with the diameter d and resistance is R is placed in a magnetic field B that is parallel to the plane of the ring. Magnetic field is parallel to the plane of the ring. Let's bring a ring into picture. Here is the ring, and magnetic field is in the plane of the ring. It's like this. So magnetic field is parallel to the plane of the ring. A voltage source with a potential difference of V naught is to be connected to 2 points on the ring. What 2 points on the ring would you choose to generate the maximum force acting on the ring from the magnetic field? This is the problem. Choice is ours. So current current can run in the ring, in the plane of the ring, and magnetic field is also in the plane of the ring. So force IL cross B is certainly directed perpendicular to the plane of the ring. In which direction? We will decide it soon. It depends on the direction of current. We have not assigned any direction to the current yet. So let's try to understand the possible solutions. One possible way to find the points corresponding to the maximum force is to take two arbitrary points whose position may be at some angle to the magnetic field vector, and obtain the formula for the total magnetic force acting on it. Then it would be possible to determine the maximal conditions for this formula. But I think this is a rather long and tedious way to solve this type of problem. Instead of going through this process, let's try to guess the answer. We are just guessing it. And when you try to guess the answer, clearly we have two choices. Either to connect the source at diametrically opposite points, to orient this diameter perpendicular to the field, like this, because orienting in any other direction rather than perpendicular to the magnetic field. There is no meaning to do something like that. So we have the first choice, like connecting the source that diametrically opposite points, and this diameter should be perpendicular to the field, or we can choose two neighboring points. That means two very close points. Also, I guess for the sake of symmetry, if this is the center of the ring, so let's choose these very two close points so that the line joining them makes a triangle, that subtends an angle alpha at the center of the ring, and alpha is very small. That means we have chosen 2 points, one of maximum length, that is a diameter perpendicular to the magnetic field, and another is a point like but yet perpendicular to the magnetic field. Point like distance, point like length, but perpendicular to the magnetic field. And we will then need to calculate the net magnetic force and compare the results. And so in the first approach, that is this, that is connected at diametrically opposite points, the current through each half of the ring is obviously, but let me do one thing first. Let me minimize this thing so that we will have sufficient area to work on this problem. So in the first approach, connecting at diametrically opposite points, the current through each of the ring is simply, call it I1, and this will be V0, the potential difference applied by the radius of each part, that is R by 2, and so it becomes 2 V0 upon R. And in this case, the force acting on the magnetic force, basically Lorentz force acting on these two segments, it can be simply determined by the projection of its length on the diameter. And so the total force, call it F1, will be I1 B multiplied by twice of this diameter, that is, call the diameter as D. If we take the diameter as D, so the distance will be 2D, and after putting the values of I1 from here, we will get the result as 4 V0 BD upon R. So in the first case, first approach, we will get the total force acting, the value of total force being 4 V0 D by R. And with the second approach, that means connecting the two neighboring points here, the force is determined by the action of the field on the small segment of the ring, because the forces affecting the other parts of the ring are practically counterbalanced. So the current in this tiny segment of the ring, call it I2, will be V0 upon R alpha R 2 pi R divided by 2 pi by alpha, that is alpha by 2 pi, because 2 pi corresponds to this, so alpha corresponds to R by 2 pi multiplied by alpha. And this is just a unitary method, nothing else. So current is this. Now we will calculate the force, magnetic force acting on this tiny segment of the ring, and let's call it F2. Then F2 can be given as I2 B multiplied by this length. We need to calculate this length. And so if this angle is alpha, this length is D by 2. R is the resistance, so I am using radius as half of the diameter, and these two angles beta are going to be the same. That means we have 2 beta plus alpha equals pi. That means beta can be written as pi by 2 minus alpha by 2, and if we use the sine formula, we can simply write d by 2, or let's call this length s, so that we can write s upon sine alpha is equal to d by 2 upon sine pi by 2 minus alpha, sine beta equal to sine pi by 2 minus alpha by 2, that is cos alpha by 2. Since alpha tends to 0, we get the value of s equals d upon 2 alpha simply. So the force being here I2b multiplied by alpha d by 2, this force. And further you can calculate that just by putting the value of I2, you will get that F2 will be equal to pi V0 BD by R. And now compare these two results. B0 BD by R is common in both the cases, V0 BD by R, and here is 4 and here is pi, so approximate value of pi is 3.14. That means this F2 is less than F1. And it turns out that the first approach yields the maximum force acting on the ring. So we solved the problem. Thank you very much for watching.